In this video, we will talk about circuit elements and then resistor combinations. So first, let's talk about the components of a circuit diagram. Here are the components for a light bulb, a single cell battery, a multi-cell battery, a wire is simply a line, a resistor is a zigzag, and there are the symbols for an open and closed switch. So this diagram here would be a diagram that shows multiple batteries and a resistor. And this is the simplest circuit that you can create that is functional and not dangerous. A circuit with no resistor is called a short circuit. Because there's nowhere for the energy to be dissipated from the battery, the wire will simply heat up and sometimes cause a fire. The long side of the terminal here is the positive side, and in the United States we use what's called conventional current, which is defined as positive charge flow. So in the U.S., we model current as positive charges, even though that's not what actually charges or what actually flows. Remember that the charges are energy carriers. The battery gives the charges potential energy. Voltage, one second. So voltage is a volt is a joule per coulomb. So as the charges go through the battery, they gain energy. And they gain energy per unit charge. And then they spend that energy in the resistor. The battery acts kind of like a pump, resupplying charges with energy. And some people like to use this, use like a water fountain analogy, where the battery or pump pumps the water up and gives it potential energy. In this analogy, that's gravitational potential energy. And then it spends that gravitational potential energy coming down, and it goes through the cycle over and over again. Notice in this model of current, the amount of charge doesn't change, but the speed of the charge or the rate of charge could change. And current, so here's voltage. Current is charge per unit time. Okay. So now let's talk about what happens when we combine resistors in series or in parallel. And I think I'm going to jump right into the examples, and then you can read these notes as needed. Okay, example 1. A 10 ohm, a 15 ohm, and a 20 ohm resistor are connected in series across a potential difference of 90 volts. So the first thing I'm going to do is I'm going to sketch this using the symbols for circuits. So here's my 90 volts. I've got a 10 ohm, 15 ohm, and a 20 ohm resistor. And I'm actually going to number these. I guess I don't need a circle. R1, R2, and R3. Find the current and the voltage across each resistor. When I set these up, what I like to do is make a table. And I'm going to number my resistors. Just trying to keep everything organized here. And there are 3 quantities that I'm interested in here. I'm interested in resistance, current, and voltage. And V equals I times R. So that reminds me of Ohm's law. I'm going to fill in my resistor quantities here. Okay, my first step in solving any problem like this is to find the equivalent resistance. The equivalent resistance in series is simply the sum of the resistors. So in this case, the equivalent resistance would be 10 plus 15 plus 20, which is 45 ohms. And once I have that equivalent resistance and I know the total voltage, I can use Ohm's law. And I'm going to use Ohm's law for the entire circuit. So I'm using the total voltage and the equivalent resistance. So to solve for I would divide both sides by 45, and I would get that the current is 2 amps. So there are 2 amps of current flowing through each resistor. So think about that for a second. If I model the current as positive charge flow, these 2 amps have nowhere else to go. They travel, all of that current travels through those 3 resistors. Once I have the current calculated, I can use my formula, V equals IR, to get the voltage. So we've got 20 volts through resistor 1, 30 volts through resistor 2, and 40 volts through resistor 3. And if I were to actually take voltmeters and put them across these resistors, I would find that the first one measured 20 volts. And what that means is that when these charges come through the wire, this 20 volts is 20 joules per coulomb. The charges are expending 20 joules for every coulomb of charge that flows through that wire. And the same for the next 2. The next one would be 30 volts, and the next one would be 40 volts. Also notice that when I sum these together, I get 90 volts. So the charge carriers, the electrons, get 90 volts, 90 joules per coulomb of charge here, and then they spend that amount of charge through the 3 resistors. All right, let's try another example. A 10 ohm, a 15 ohm, and a 20 ohm resistor are connected in parallel across a potential difference of 90 volts. Find the current and resistance through each resistor. Okay, so we've got 90 volts, 10 ohms, 15 ohms, 20 ohms. I'm going to name them again. 1, 2, 3. I'm going to make another chart. This one might be even a little bit easier, but I'll follow the procedure anyway. Okay, so again, R times I equals V. And my resistors, 10, 15, and 20. Now, in this case, the voltage across each resistor is 90 volts. That is a property of parallel circuits. So you may notice in this top one, the current was constant in series. And now what we see in parallel is that the voltage is constant. So since I know that the voltage across each one of these is 90 volts, it's pretty simple to solve this using Ohm's law. 90 divided by 10 is 9. 90 divided by 15 is 6. 90 divided by 20 is 4.5 volts. Later, we are going to solve some more complex resistor combinations, and in preparation for that, I'd like to show you something else. What if we wanted to solve this one with similar steps to what we did up here? Our first step in the series problem was to solve for the equivalent resistance. The formula for equivalent resistance in parallel is reciprocal. 1 over the equivalent resistance for the entire circuit equals 1 over R1 plus 1 over R2, and you can keep going for as many resistors as you have. So for this one, we would say the 1 over the equivalent resistance is equal to 1 over 10 plus 1 over 15 plus 1 over 20. At this point, I would consider solving this with the x minus, the the reciprocal button on your calculator. Because really what this is 10 to the negative first plus 15, to the negative first plus 20 to the negative first, all to the negative first. If you're like me and you love a good fraction, you could also do 3/30 plus 2/30, not 30ths, 60ths. Let me try that again. 6/60 plus 4/60 plus 3/60 equals 13/60. Wait, is that right? All right, I'm not sure. Well, my brain's not firing all together here, but okay, so the equivalent resistance then would be 60 over 13. And then to find the total current, I would take the total voltage divided by the equivalent resistance. Again, I'm just taking V equals IR and rearranging it. And so that would be 90 times 13 over 60, which would be, 1.5 times 13, which is 19.5 amps. And notice, that's good. Notice when I add these together, 9 plus 6 plus 4.5, if I add down, I get 19.5 amps. Let's think about what's happening then. In this part of the circuit here, 19.5 amps are flowing. Then the current splits. And through each resistor, we have a different amount of current. We've got, oh my goodness, I wrote volts. This is amps. Pardon me. Okay, this is 9 amps through resistor 1, 6 amps through resistor 2, and 4.5 amps through resistor 3. Notice that the current splits inversely proportional to the resistance. In other words, the smallest resistor gets the biggest current, and the biggest resistor gets the smallest current. That's because it's harder for the current to push through this larger resistor. That's what resistance means. That's also why this is an inverse formula. Okay, so those are your first two examples, and I'll see you next time for more complex